processor performance. So we can write that expression. We can say that if we multiply okay, let me refresh my memory here. Okay, so the number of faults that would be found during one execution would be given by the derivative of this multiplied by t sub s minus represent the fact that the number of faults present decreases, multiplied by the single execution time. So the faults that would be found in a single execution would be given by t sub s multiplied by the number of faults present there. And here we are assuming t sub s is a constant. And we can rewrite this. And if you want to rewrite this, I will introduce a notation. Here's a notation that I'm introducing. And the reason I'm introducing this notation is that I want to get this expression in a form that is often used. So let me use this notation. Let me use k to represent k sub s multiplied by TL by TS. So I'm going to replace this term and this term by k and TL. So that will allow me to do this. And this factor is, we are going to refer to that as beta 1. So that would be one of our parameters. Now here, K is called fault exposure ratio. It was introduced by John Musa. And he had argued that K would not depend on program size. And that we can write it this way. So here we get this differential equation. And so basically we are assuming that K is a constant. It does not depend on program size, that as Musa has argued. And we could assume that it doesn't depend on anything. So it basically is a measure that is dependent on your software testing strategy. So for a better testing strategy, K would be higher. We actually did a study on fault exposure ratio. I think we will include a reference near the end. And we found that the assumption that the fault exposure ratio does not change is not exactly true. And we have shown that K actually depends on testing strategy. And it depends on where in the testing you are. And we looked at the variation of K with how it varies as testing progresses. But I will let you look at the paper if you are interested in it later. So let's keep things simple and continue with this. So solving this, we get, now this is your well-known type of differential equation. We have come across this type of differential equation before. You get nt is equal to n0 e raised to minus beta 1t. And we can also get equivalent to this, mu t is equal to beta 0 1 minus a raised to minus beta 1t, where beta 0 is a constant. Okay, you can easily figure out what is the meaning of beta 0. What happens when t approaches infinity? Notice that when t approaches infinity, this term is 0. So mu t is equal to beta 0. So that means the total number of faults you expect to find eventually, if you keep testing for a finite time, would be beta 0. So beta 0 is in effect the initial number of faults you started with. So this is your initial number of faults. Let us write down that argument here. As t approaches infinity, mu t approaches beta 0, and hence beta 0 is the initial number of defects. Incidentally, that means that you can estimate beta 0 in a simple way. Okay, this is the initial number of defects. So all you need to do is to estimate the initial defect density and multiply it with the software size. You know the software size. You can measure it using one of the packages. So that will give you what is the initial number of defects, an estimate of it. Estimating beta 1 will take a little bit more work, and but I will have some comment on that. Or equivalently, notice that this equation, and this equation, they all have the same information. If I give you one, you should be able to get the other one. So notice that this is the derivative of this. So if you take derivative of this, you will get this. Now this is referred to as a finite faults model, because at time approaches infinity, this will approach a finite number. So this is called a finite fault model. In other words, okay, there are some fault models that are supposed to be infinite fault models. Do you think it makes sense? That number of defects in the piece of software is infinite? We will come back to that question. So that's an interesting question, and I think there should be a different perspective, which I will introduce later. Now here we have assumed that there are no new defects that are generated during debugging. When you find a fault, you remove the fault and keep on removing, and if you keep process, if you will keep at it, eventually beta 0 is the number of faults that you will find. In practice, they have found that whenever you do debugging, in 5% of the cases you replace a fault by another fault. So if you started with 100 faults, by the time they are all found, if you will ever find all of them, you're going to find 105. because there would be 5 for that would be get introduced. But for statistical purposes, that is still a reasonable approximation. Okay, so instead of 100, it's 105. It's not a big deal. Now, okay, who came up with this model? Zelensky and Moranda in 1971, Schumann in 1971, Uel and Okimoto in 1979, and Musa in 75 and 80. So you will come across a Zelensky-Moranda model, which is the same as this model, or this might be referred to as the Schumann model. So depending on whose student you are talking to. So if you are talking to a student or student of Schumann, make sure that you refer to this as the Schumann model. But we are going to call it the exponential model because it has the basic exponential thing. So if you will make a plot, here's a plot, that is here time, and here is the failure intensity, which is lambda t. So according to the model, the failure intensity will now decline this way, because this is of course given by beta 0, beta 1 multiplied by e raised to minus beta 1t. And this here, of course, is going to be your beta 0, beta 1. Sometimes beta 0 and beta 1, they are referred to as lambda sub 0. So sometimes they will say lambda t is equal to lambda 0 e raised to minus beta 1t, which is the same thing, just different format. And here is mu. Remember, mu is the total number of falls that would be found by time t. So here is mu t. And here is time. So it will approach this. And here, it will approach this here. And this, of course, is, let me move this up here, is your beta c. So it will asymptotically approach beta 0. Okay, now, as I was saying, one good thing behind this model, okay, we still have a couple of minutes, is that the parameters have a nice meaning. We know the meaning of beta 0. And let me give you the meaning for beta 1. So we are not going to have the class this coming Tuesday. I will be back here on Thursday. But there will be something for you to do. So tomorrow, check for a homework, a quiz, and a reading assignment. So reading assignment is supposed to use the time for Tuesday. Okay, what beta 1, remember that we had said it's equal to t divided by TL. And k is supposed to be a constant, and TL actually stands for the linear execution time. So TL is the execution time it will take if you would execute each instruction once and only once. The TL is not the real execution time, because typically in a program you have some loops. So some instructions that are executed many times, and then you have some branches. Sometimes some part of the code is not executed at all, because it's executed when you do if then else. But if you would execute each instruction once and only once, The total execution time is going to be TL